I'm getting a lot of questions about coordinate transformations and the three types of coordinate systems that we have introduced so far in the course. This is pretty much lecture 6 in MIU 100. And what I thought to do is a quick overview of the coordinate systems, recognizing that they often prove challenging, and trying to emphasize the fact that we are looking at the same thing. And finally, to go through a relatively simple example. But if you're looking for more complex examples, by the way, please refer in terms of your lectures between lectures 3 and 6. And that may be helpful to look at the same thing as well. The important thing here is that the components of each coordinate systems change, but the magnitude does not. And so we have a group of vectors that come out of this. So for position, r is equal to xi, yj, zk in the Cartesian system. Magnitude s just along the path. R is equal to rer in an r-theta coordinate. It gets, when we take the derivative with respect to time, we get velocity, and we get vx in the I direction, vy in the j direction, vz in the k direction for a Cartesian system, the rectilinear system. If we look at an NT system, it's pretty good. It's just speed in the tangential direction, which kind of makes sense. Velocity is always going to be tangential to the path. In an r-theta system, it's a little bit more because we now see the first effect of a derivative of the unit vector, e sub r. And we end up with a term that goes theta dot e theta. So if you're interested in that discussion, I would suggest looking back at lecture 6. But we end up with r dot er plus r theta dot e theta. Finally, we have acceleration. Again, relatively straightforward. Lots of component parts, ax in the I direction, ay in the j direction, az in the k. Acceleration in an NT system, again, sees the effect of the derivative because of the change in direction of e sub t. And so you have acceleration tangential e sub t and acceleration normal e sub n. Acceleration tangential is dv dt. Acceleration normal is just going to be v squared divided by rho. Acceleration is equal to acceleration r in the r direction plus acceleration theta in the theta direction for the r theta system. And that's equal to r double dot, which is the second derivative with respect to time of r, minus r theta dot squared, theta dot being d theta dt. Acceleration theta is r theta double dot, second derivative of theta with respect to time, and plus twice r dot theta dot, r dot dr dt, d theta dt for theta dot. So you have a whole bunch of terms that have appeared. The equations look more complex, but really, again, it's kind of important that I emphasize that we are, in fact, looking at the same thing in multiple ways. So coordinates do not modify position, velocity, or acceleration. The scalar components, the components of each of their descriptors, do change. So they're different in the three coordinate systems. So here I have a particle that is in the process of moving under projectile motion. At the very top of its motion, it has a velocity to the right, v, and a g acting downward. And v sub y in this case would be equal to 0. Position is just going to be r, which is going to be x and y. And r is defined to the particle. For an NT system, you don't describe it in terms of vectors, you describe it in terms of magnitude, and that's the magnitude of the path from the origin, s. For an r-theta system, it's just r to the particle, and theta is the angle with respect to the horizontal. And it's measured counterclockwise. At this high position, velocity x is equal to velocity tangential sort of being synonymous, and it's v. For r and theta, you're going to have vr, ur, and v theta, u theta acting in the respective directions with respect to r. And we'll go into more detail later on this. Acceleration y and acceleration normal at this top position where the particle has reached the highest point is just acting straight down, so acceleration y equals acceleration n. But the magnitudes, and I'll show that again later in a few minutes. However, as you move along, acceleration tangential and acceleration normal will change, and you'll have components of tangential acceleration as you move along the path. Acceleration theta and acceleration r are negative because they're pointing inwards and in the clockwise direction. Caesar has sent you to conquer a group of indomitable Gauls. You've been provided with a catapult and given the following information. Can you hit the village wall between 1 to 3 meters? V0 is equal to 25 meters per second. Theta is equal to 25 degrees. You are at 2 meters above ground is where you launch, and you want to hit between 1 to 3 meters. You have the initial conditions and all of the information you need to start out. So we can start out looking at a Cartesian system. V0 x is V0 cos theta, V0 y is V0 sine theta. As usual, we assume no horizontal acceleration, so the final position is equal to x0 plus V0 x tf plus 1/2 ax tf squared. Ax is equal to 0, no horizontal, and x0 I've defined as 0 as the starting point. Time of flight then is just V0 x divided by the total distance, and you end up with 2.21 seconds. If you put that time into y and you calculate how long it takes you to get to the final point and recognize that g is acting downward, so it's negative in this part of the problem, and it's equal to minus 9.81 meters per second squared. You'll solve through and you get yf is equal to 1.43 meters. What is the radius of curvature at the highest point in the flight? Again, this is a problem you've seen in some form already, I think, in your lectures. I did something like this in lecture 5 in my case. So again, same starting position, same information, but you're starting off at the highest point. It's an NT problem, so I want to solve for that, and I recognize that kappa h is the height. G is acting downwards. At the highest point, acceleration x, well, acceleration x is equal to 0 everywhere. Acceleration y is equal to minus g. And here I am including direction. So when I go to an, g is pointing down towards the center of curvature, and acceleration normal is also going to be positive. Acceleration tangential remains 0 because it's at the top of its flight. Note the signs, and this is really important, and one of the reasons why it's useful to draw out these images. At the high point, Vx is equal to V0 cos theta, and Vy is equal to 0. So V is equal to Vx, so the speed magnitude is equal to the velocity in the x direction. For the normal accelerations, v squared divided by rho, substitute in, rho is equal to v squared divided by a sub n, and you get rho is equal to 52.3 meters. All right, no problem. Everything is sort of worked out so far. It's all kind of sensible. Let's look at the last part. What are the components of acceleration in r-theta coordinates at the point of release, point A? So you see point A there. I'm going to show v0 and theta. I'm going to have an xy coordinate system that is shown in there. And I'm going to also define E sub r and E sub theta. And you'll notice E sub r is pointing outwards from point A, essentially. And E theta is pointing in the counterclockwise direction. So this is where I got to start with. I have a path of that particle that's a parabola, so somewhere along there I have G. And I can define r with respect to my origin. So r is there, and er, E theta at that next position looks like that. So if I take the g and beta out and sort of blow it up, I can then describe the acceleration in the r direction and acceleration in the theta direction. Acceleration theta is equal to minus g cos beta because it's going clockwise, and ar is equal to minus g sine beta because it's pointing in towards the origin. R double dot minus r theta dot squared equals ar, which is equal to minus g sine beta. R theta double dot plus twice r dot theta dot equals a theta minus g cos beta. So I'm using definitions on the left-hand side, which are definitions we've derived and arise out of these unit vector derivatives. And at point A, the way I've defined everything, r at 0 is equal to h, the height. Theta at 0 is equal to pi over 2. Okay, great. V naught is equal to V naught sine theta ER minus V naught cos theta E theta. So taking those values, putting it in, I know that V at 0 is equal to R dot ER minus R theta dot E theta. Again, definition and recognizing that I started out with the position vector RER, took a derivative, and I got this expression for V. Equating the like terms, R dot equals V naught sine theta, R theta dot equals minus V naught cos theta. R dot V naught sine theta equals is V sub R, and theta dot is equal to minus V naught cos theta divided by R, and R in this case is equal to H, excuse me, and that's equal to minus V naught cos theta over H. So the important thing when you're thinking about this is, can I solve these problems with any of the coordinate systems? Sure, you can absolutely do that, but sometimes this choice will make things more complex and unnecessarily complex. With cylindrical polar coordinates, this problem is ill-posed if A is at the origin. So you'll notice that I have an origin down at the ground, but A is 2 meters up. I believe that was what it was. In this case, R is equal to, if I had not done that, if I had placed it at A, R would be equal to 0. Theta is arbitrary because it can't really be defined. And then that leads to theta dot being undefined, and that's the problem with zeros. When using this coordinate, just as a piece of advice, do not place the origin with the initial condition positions. Trajectory and solutions are true in all coordinate systems, so they have to be the same. Choice of coordinates do not change physics. Okay, and again, I kind of repeat this because I think it's one of the more important takeaways from this. Coordinates do not change the physics, and this is one of the things that makes dynamics interesting. You have math that you're doing, but you're also worried about the physics of everything. Geometry is hard until you practice, and you certainly can handle it, but you need to do examples, and you need to be confident of how to get those thetas and betas and everything else so that you have everything correctly done. As much as possible, and one of the things you should have noticed is that you need to draw. You need to draw. I can't say that enough. But the other thing too is that keep your units. Now you'll notice that often in these calculations, I've done things with variables. Variables make things a lot easier for me, and then I put my units at the end. So that also would be a helpful piece of advice to think about. Thank you very much, and I look forward to seeing you in the future.